So now we're going to start the last section. Actually, right before we do it, just wanted to take note, this bullet, it actually does pertain to 7.2, the last little bit about electrolytes. Basically something that I had reiterated at the end of the last sheet, which was saying that an ion in aqueous solution, water solution that means, that conducts electricity is an electrolyte. It's just a definition. Okay, so just remember what an electrolyte is. Okay, next thing. 7.4, metallic bonds and the properties of metals. Well, the two things we're going to look at right now are going to be how do metals conduct electricity, and why is it that when you apply a force to metals, they bend as opposed to shatter, which is what we saw with ionic compounds. So again, take a second, read through the objectives. Once you've done that, this is pretty much just explanation, so we'll just bear through it. Metallic bonds and the properties of metals. Metals are not ionic but share several properties with ionic compounds. Within the crowded lattice, the outer energy levels of metal atoms overlap. What that means is the following. If I have one atom of a metal here, here's the proton for it. The energy levels for it, particularly the outer ones, let's just say that this atom happens to have electrons going out to n equals 3, the third energy level. The valence electrons in the third energy levels will overlap with adjacent atoms. So let's say this is another atom here. So here's two different atoms, atom 1, atom 2, and what happens is that the third energy level of 1, where the valence electrons lie, will overlap with the third valence energy level of another atom, where their valence electrons lie. So that's basically what it's saying here. Within the crowded lattice, the outer energy levels of metals overlap. The electron C model proposes that all metal atoms in a metallic solid contribute their valence electrons to form a sea of electrons. So imagine for a second back here that you have not only these two atoms, but then another atom below here, in front, behind, etc. So with all of this overlap of their outer energy levels and eventually their valence electrons, you create this, as the name implies, a sea or ocean of electrons. These electrons are free to move around and are referred to as delocalized electrons. Why are they called delocalized? Well, look at the word delocalized. The prefix de meaning not, localized meaning set in a certain small region. These electrons are not set in a specific region. They are delocalized. They form a metallic cation. So here's what happens. If you look at this diagram here, this diagram is the electron C model. You have the sea of electrons, which is your valence electrons, that overlap. So the energy level of, let's say, this atom here can come out here, and it overlaps with the energy levels over here. So the valence electrons, for one, can actually swim or float across areas, hence the delocalized electrons. If you look here, metallic bond is the attraction of metallic cations for delocalized electrons. Well, how did metallic cations form? You have to realize is that these valence electrons, if they start to float, well, if this atom happens to lose even one single valence electrons due to just random floating, he now has a positive charge. And the same happens all across the board. At any given instant, what happens is that all of these atoms are going to get an instantaneous positive charge, and perhaps they get negative again. They gain valence electrons, etc. again. But because these valence electrons can float around, you're going to get this cation effect, ionization effect for these metal atoms forming a metal cation. Hopefully that makes some sense. Otherwise, this right here shows the electron C model, why it's an ocean of electrons with these metal cations floating around. So how does that pertain to various properties of metal? First off, you should know that metals have a very high boiling point. They are much more extreme than melting points because of the energy required to separate atoms from the group of cations and electrons. Here's what that means. Take a look at any of these elements, metals. Let's use something like aluminum because we're pretty familiar with it, and we'll compare it to copper as well. The melting point for aluminum, 660 degrees Celsius, pretty high, but not terribly high. But look at the jump from melting point to boiling point. The jump is going from 660 degrees Celsius to 2,467 degrees Celsius. And even copper, 1,083 degrees Celsius to 2,570 degrees Celsius. So in order to actually get aluminum, copper, silver, barium, etc. to boil, you need a tremendous amount of energy. Why is that? Well, look back at the electron C model. In order to boil off, you need to actually take this atom and vaporize it. In order for you to vaporize it, you actually have to take this metal cation and separate it or pull it out of the sea of electrons. Well, you can probably figure out that it's going to require a lot of energy. Wouldn't it require a lot of energy to start getting these metal cations to kind of shift around and move around, hence taking on a liquid state, which is the melting process? But to actually get it from liquid to actually vapor state, all right, that's going to take a tremendous amount of energy, as is evidenced here. So the electron C model explains why metals can have a lower, relatively low boiling point, but an extremely high boiling point. Okay. It also explains why metals are malleable, because they can be hammered into sheets. It also explains why metals are ductile, because they can be drawn into wires. Unlike ions, if you remember, when we apply a force here, okay, by applying a force into this for ionic compounds, what happens is that there's an realignment of cations and anions. In this one, there's a generalized region of sea of electrons. So if you hammer or put a force downward here, what happens is that all you're doing is shifting the metal cations, but they remain inside the sea of electrons. That allows metals to, again, be malleable, meaning able to be hammered into different shapes, and ductile. Ductile meaning that they can be drawn into wires. Okay, because they have these atoms that are able to shift around and move around, but still stay within the sea of electrons. Okay, that's what creates that. All right, the next sheet basically demonstrates that. You'll see it says here, an external force hits it. What happens is that the metal is simply deformed because you're shifting the metal cations, but they still remain within this sea of electrons. Okay, so mobile electrons, aka delocalized electrons, around the cations make metals good conductors of electricity and heat. How is that? Well, if you recall, electricity is going to be transference of electrons. Well, if this sea of electrons allows for valence electrons to float around, obviously, if you have electricity, that electricity can transfer from one area to the other. That's why metals can conduct electricity. Okay, obviously some metals are better conductors than others. That is going to be dependent upon the how good the quote-unquote sea of electrons is for electricity. All right, next. As the number of delocalized electrons increases, so does the hardness and strength. What does that mean? That means that if you have more and more electrons inside of this sea, that means more and more overlap. Okay, the hardness and strength of the atoms of the metal starts to increase. So if you think about it for a moment, that actually makes sense. If you have so much negativity in this blue region here, okay, that means that it's going to take more energy to actually shift the position of this positive metal cation. Okay, if you have less electrons there, because you have less of an opposite charge, it's easier to shift those positive cations. So that's what this bullet right here. As the number of delocalized electrons increase, so does the hardness and strength. Hopefully that makes sense. And finally, as a last vocab, an alloy is a mixture of elements that has metallic properties. Common examples of alloys are going to be like stainless steel. Stainless steel is going to be an alloy. Actually, no, stainless steel is a mixture. My apologies. Another example for an alloy would be something like 14-karat gold. Okay, pure gold is very malleable, very soft. So what they do is they mix it with other metals, so that way it's going to take on a stronger characteristic. Okay, but that's pretty much it as far as notes go on this stuff. Alright, hopefully it wasn't too bad. And again, good luck with studying all this stuff. I will try to keep my access to email and check it on Sunday and Monday, since we have Monday off. Any kind of question, please email me. Okay, so good luck with that and have fun. Thanks.